Hi, my name is Jasmine Vu, and I'm studying biomedical engineering at Northwestern University. Imagine if there's a way we can take detailed pictures of any part of the human body, from the brain to the heart to all the bones in your foot. Nowadays, we do have such a technique, and it is called MRI. MRI can produce high-resolution images and help us better understand the structure or function of many different parts in the human body. For most patients, MRI is a safe imaging method. However, for patients who do have a long metal implant inside of them, such as a pacemaker or a neurostimulator, there are additional safety risks during a standard MRI exam. In fact, up to 75% of patients with these implants will need one, if not more, MRIs during their lifetime. Unfortunately, MRI is inaccessible to most of these patients. This is because the tissue immediately surrounding the implant can heat up and result in permanent burns inside the body. This thermal injury is known as an MRI-induced radiofrequency, or RF, heating, and it is caused by the interaction between the electric fields that are being produced by the MRI machine and the long metal implant. My research is focused on improving the safety and accessibility of MRI for patients with these long metal implants. In my work, I'm trying to reduce the amount of RF heating around a specific type of implant known as a deep brain stimulation, or DBS, device. During a DBS surgery, a long insulated wire, which can also be called a lead, is inserted inside the brain. When a neurosurgeon performs this operation, the part of the lead that's inside the brain needs to target the correct anatomical structure. On the other hand, the portion of the lead that's outside of the brain is randomly placed on the skull. One surgeon may place the lead like this, or potentially even like this. This randomness makes it very difficult to predict how much the tissue around the implant can heat up during an MRI exam. But what we do know from previous studies is that the location and the placement of the lead has a very important effect on the amount of RF heating during an MRI. In my research, I'm trying to optimize for the placement of the portion of the lead that's inserted outside of the brain in order to reduce the amount of RF heating during an MRI. The goal of this work is to make MRI possible for these patients and to create a consistent method for implanting the extracranial DBS lead across neurosurgeons. Not only will this work be efficient, but it will not interfere with the treatment via the DBS device or the MR imaging. This work will open doors to standard of care MRI for these patients. For more information, please visit the website below, and thank you for watching.